Welcome back. We're on the Module 3 Practice Test Part 2 Video Portion 3. 14 says Dylan invested $600 into a savings account at a 1.6% interest rate. He made no deposits or withdrawals on the account for 2 years. The interest was compounded annually, supplying to the nearest cent the balance of the account after 2 years. So first you got to decide what type of an account is it? What type of function is it? Linear or exponential? Percent should tell you exponential. Since it's money in an account and we know it's growing, that means it's exponential growth, so we'll use that A times 1 plus R formula. Remember, A is our start. R is that interest rate, but we need to convert it to a decimal, so 1.6 divided by 100, and it'll give you 0.016. And T is our time. So plugging that in, we just need to then find an answer. How much money is in this account? So 600 times 1 plus 0.016 to 2. $619, and then to the nearest cent, 35 cents. Next page. Rachel and Mark were given information shown below about bacteria growing in a petri dish in their biology class. X is the number of hours. B of X is the number of bacteria. Rachel wants to model it with a linear function. Mark wants to use exponential. Which is the better choice and why? Remember, linear has that constant rate of change. So the simplest thing that we can do is figure out how did it change between each group from 220 to 280. You can always do the 280 minus the 220 in your calculator if you need the assistance. So see is that I added 60. So moving to my next group, from 350 to 280. Let's see, 70. So it's changing, and when we do our next group, it's changing some more. Now we're at a difference of 90, so it's not even, it's like the amount of difference is doubling every time. So that tells you right there it cannot be linear. It must be exponential. And the simplest reason is because it is not a constant rate of change. Right. 16. The number of carbon atoms in the fossil is given by this function, where X is the number of years since it has been discovered. What is the percent of change each year, and explain how you arrived at your answer. So remember, with these exponential functions, we get that A times B to the X format, or A times 1 plus R, or A times the 1 minus R. With B, we know if it's growth, if B is greater than 1, we know it's decay if B is less than 1. So looking at this portion of my formula, 0.95 I know is less than 1, so I know that this is exponential decay. Okay, so 0.95 is less than 1, makes exponential decay. So now I'm going to use the A times the 1 minus R format of the function to figure out that percentage. So I took 1 minus R and I plugged in whatever R is to get this answer of 0.95 that's in the formula. Solving for R, if I subtract 1, negative R is equal to a negative 0.05 divided by negative 1. R is equal to 0.05. Convert it back into a percent by multiplying by 100. So it's a 5% rate of change per year. And your work, and like this little bit of sidebar information that I did is enough. Okay, I thought it through. It's exponential decay. I used this formula and I solved it. Multiplied by 100 and I got there. So that'll work. 17. We need to graph both of these functions on the axes and then state which function has a greater value when x equals 20. So one at a time, you will want to put these into your y equals and create yourself a table to plot it. And you're looking at our graph, I see it's just this quadrant one. It's all positive values of x and y. So you're just graphing from 0 on up from your x column. So pause it and then come back and take a look. So put f of x in my y equals. This is my table of values. And I'm just graphing them. In your paper it'll be a little easier to graph because everything will fit. I see I can't fit the 5-point in. It goes beyond the graph, but it gives me an idea of like where I need to go. I'm going to connect as neatly as I can. Put my arrow and label. Again, you need to pause, put g of x into your y equals, and also get a set of values. Again, I put g of x into my y equals, and I look at my table. So g of x starts at 0, 1, and then 1, 2, then 2, 4. They're going to cross each other here. 3, 8, it's still a little bit below f of x. 4, 16, they're crossing each other again, and then 5, 32. It's still not going to fit, and it's actually greater than it was on f of x. As I try to wrap this up. Not as neat as I would like, especially because I can't fit it all on the board to see it. Hopefully yours is a little neater. So just based on that though, what I've seen just from 0 to 5, let's see is that first g of x is higher. Then they cross and are equal, and f of x is higher. Then they cross and are equal, g of x is higher, and in fact that's how it would remain. If you put them both in your calculator on forever, you would see that. But also looking at the difference, this is a quadratic function, and this is an exponential. If you are comparing an exponential function with any other type of function, eventually the exponential function will be greater. So g of x is going to have a greater value when x equals 20. You can describe it off your graph, or you can explain that because an exponential function will always outgrow other functions. That takes care of this question. Next page. An application developer released a new app to be downloaded. The table below gives the number of downloads in the first 4 weeks after the launch of the app. Write an exponential equation that models these data. If you don't have to work hard, we're going to use the stat function. And to do exponential, that is stat calc 0. I'm pulling up the calculator. I'm going to stat and edit. Clear your L1 and L2. And input your data. Then stat calc 0, exponential regression. Make it calculate. They didn't give us much information, but luckily these are all rounded. You don't have to worry about it. So y is equal to 80 times 1.5 to the x. Now we must use it. Use the model to predict how many downloads the developer would expect in the 26th week if the trend continues, rounding it to the nearest download. So 80 times 1.5 to the 26th. To the nearest download, I see 3,030,140. So now we have a question. Would it be reasonable to use this model to predict the number of downloads past 1 year? If you stick with basic understanding of apps, apps go in and out of fashion like pretty quickly. And then also just think about how great this number already is in half of a year. Imagine where it will be by a full year. There's not enough people for that either. So you can do something to that effect. No. Apps go out of fashion and downloads slow down. Or there's not enough people to match the numbers. Something that makes sense to you. 19, and then 20, and 21. I think so. I don't have to rush. We're going to stop here. Look for a part 4 video.